Ah, nice.
All right, guys. I've been thinking about. With all the years I've been teaching, I've been trying to always find different ways to get the information to you guys, so you can understand it. It seems like something simple here, but I have an idea where I want to go. So we're going to start talking a little bit about wiring diagrams. So I'm not going to just start off with my usual diagram lecture where I have a whole diagram machine. The current flows here, and this is. Let's break down some of the parts of the diagram first, and what do we need to look at? So we got a lot of parts here, and they were all on this sheet here. We have like this, came out of the book with all the symbols on it. You guys all have that in your basic electricity folder. I also have it on the TMN website for download. These are all different symbols. There are more symbols than this. I just grabbed a bunch of them, and I want to talk about, first of all, what they are, and then I want to talk about the circuit and what's important about them and what we need to know just by looking at the symbols. So the first thing is here, we got a lot of controls and loads. What is a control? Just simple terms. What is a control? And don't say your wife. No, but what is a control?
To on and off.
Okay, so give me an example of a part that is a control.
The switch.
A switch. Okay. So in this row, are there any switches in this row on the left-hand side?
Yes.
Yes. Give me an example of a switch. Number 1, 2, 3, 4, 5, 6, 7. Give me a number.
Two.
Okay. So number 2 is a switch. Well, we'll call it a control. Oops. Spell wrong. And I'll put the loads over here. And I'm going to explain to you what's important about this, and that's why I'm bringing them out, because we need to know that. So the light bulb, right?
No.
What type of light bulb is that?
Germicide. It's a herbicide.
It's a what?
It's a germicide. It's a
Okay.
germicide.
So what do you mean by germicide?
I just know that because of the diagram, but I think
Okay.
it kills
Does it?
bacteria or something.
Okay.
Like that.
So where would I find that type of light?
Ultraviolet or something like that.
In my central air, because of COVID, in my office, everybody in the office was, COVID. So hold on. I bought this ultraviolet light.
Yeah.
You open it up where the AC coil is, and you put it inside the coil, or inside next to the AC coil, and you connect it to the power. And that ultraviolet light kills all the germs as it's circulating the air around your office. It also helps reduce people from getting cold. Like if I go into the office and I'm sick, I can bring the germs to everybody in the office, but if I have this ultraviolet light, it's not going to prevent everybody from getting sick, but it will reduce everybody in your office from getting sick, so it's actually a benefit. What about a barber? You ever been to a barber shop and they got that little metal box and
Yeah,
they keep the
the
combs and the
stuff up
scissors
there.
and everything in? It's got that like purple, blue light. That's an
Germs.
ultraviolet light.
Oh.
So what's the difference between, what's the difference between this light and this light? Besides the fact that, let me just rotate this one. Oops.
Is the dot because of the dot is the difference?
The dot.
Yeah.
What is the dot mean? What does it mean, the dot? The dot denotes that there is a gas inside that bulb.
Okay.
So a regular light bulb, like, let me just grab one of these bulbs off the board here real quick.
The incandescent.
A regular light bulb like this has a little metal filament
Incandescent.
here, okay? And power comes in through the center, goes up through one of the two legs going up, goes through that little filament wire, comes back down, and you can almost look this little tiny dot there where they solder it to this piece. Now they put this glass bulb in there and they pull a vacuum to get all the air out when they put it together. It's sealed with a vacuum. Why do you think they put a vacuum inside the bulb?
It should dry.
Burn out the element.
The little filament there with the air will cause it to go bad prematurely. Okay, so putting a vacuum causes the bulb to have a longer lifespan. Okay, you've all probably unscrewed a light bulb that's been on. It's really, really hot, so you gotta be careful of that. So a germicidal lamp, instead of using a little tiny wire, a lot of times it's just two prongs sticking up in the air, and the gas in between, the electricity comes here and actually flows through the air, through the gas, to the other point. Our fluorescent light bulbs that we have here, where we have one of them, can someone find me my
Yeah.
fluorescent light
It's
bulb?
right down
The
the
third one in
second-
the last,
Where?
the last column,
In the
the
middle.
third
This
one,
last one?
the third one.
That is not a
No, it's
fluorescent.
right
Ah, no,
there.
fluorescent is this,
No.
it is.
Which column? One,
Right
two,
there, right
three,
there, you
four.
just pass it, the second.
Row 1, 2, 3,
Second
4.
Row two.
This one?
Right now, right there.
This
Yeah.
one?
Yeah.
Yeah.
Okay, so I'm gonna put it over here because it's a load. And basically, fluorescent bulb has two heating elements on both ends.
And the gas in between.
Hey.
It just turned.
I don't know.
Mm.
So anyways, it has two heating elements and they heat the gas and the gas excites and glows. Okay, so the dot means there's gas inside of there. So this is a load, this is a load,
The neon
and this is a load.
and the neon too.
Now where's the neon one?
Is the last column, second.
Okay, and where would you see a neon bulb?
Ah, everywhere, offices, houses.
Outside the lights.
Bars.
Bars.
Ah.
You know, like Miller Lite beer or Bud Light, and they got the tubes that are glowing. That's
Sometimes
neon.
they have it in trucks, cars.
I'm sorry?
LED lights.
Not LED, but
Neon.
there is an LED light there. We'll talk about them another day. But we really don't use neon lights in our appliances, okay? We use fluorescent and incandescent, which are the two main ones. But those are loads. Loads are something in the diagram or the appliance that uses the electricity. Like a solenoid or a motor creates a magnetic field, causes it to run or do something, where a control is what turns it on or off. You got a question?
Yeah, so the LED light was considered a regular bulb light?
No, actually an LED light, I didn't put it here because I don't have it in my list of symbols, but an LED light is a diode. Light emitting diode. That's what the letter LED stands for. And those are like your little Christmas tree lights.
Little ones. They use them in some appliances now.
You know, like when you turn on a stove and you got this little orange light there that tells you surface is hot or the burner's on? They're usually like these LEDs here, okay?
So that would consider a load too.
That is a load, yeah. I just didn't add it because I didn't have it in the list of symbols. I went in the book and I had to grab every one of these images and put them in this presentation here. So anyways, I'm just gonna eliminate this because I don't wanna. Okay, so let's finish with the loads first. Okay, we got this one. Is there any other loads that you see here? Let's start with this column here. Is there any other loads in this first column on the
Yes,
left?
the first one.
Okay, what is this?
Shit, it's a heating element.
No, it's not.
No, it's
Resistor.
It starts with a T.
timer.
No. What'd you say?
Thermistor.
Thermistor
Yes.
or thermostat?
Thermistor.
Thermistor. What is a thermistor?
It's a switch.
No, a thermistor is a resistor that changes value on temperature. I don't know how many of my videos I talk about them.
Yes, it's
But-
the same thing you use in your car.
This is connected to a control board. Okay, like if I gave you this soda right here and walked up to one of you and said, "Hey, is this soda hot or cold?" What are you gonna do? You're gonna grab it with your hand. Oh, it's cold. Well, your mind is what's telling you it's cold, but your hand is what's sensing it, and that sensing is going back here to your mind telling you, "Oh, your drink is cold." So a thermistor is like your hand, and a computer board is your brain. So the brain is watching this sensor, and the value of that sensor changes based on temperature. It may be 50 ohms at one time, and as it gets hotter, the resistance starts going up, and the board watches that and says, hey, at 50 ohms, it's 100 degrees, but at 150 ohms, it's now 1,000 degrees or something like that. And so that's how the control board knows what's going on inside these appliances. You don't normally find thermistors on machines with mechanical timers. Now, they did have some of them where they would have a small little board like on a washing machine, and they sense the temperature of the water, and that little board just controlled the water valves. But now, as machines start evolving, all of them eventually are going to be eliminating timers altogether. Eventually, you'll never see a timer. Everything's going electronic. Okay? So that thermistor is a sensor, or it's a load because it has a resistance value, and its value can change, and it has a job to do. Okay? What about this part here?
Shit. I know.
Is that a load or a control?
It's control.
Okay, what type of control is it?
Shit, I know.
That's a switch too?
It is a switch. It's a type of switch.
Is that thermal?
It's a thermal what? It's not the thermistor. What was the other word?
No,
Switch.
Thermostat. A thermostat. That's a thermostat too. The top one. Power goes in and out through those two dots. Those little circles are telling you where the wires connect to the part. And this is what we're going to do in the next screen. And power comes in, goes through this little switch and out. This piece is telling me that's like the sensor of the heat. Okay? So if it gets hot, it pushes it and opens the switch up.
Yeah.
And then it closes back again. So if we looked...
Oops.
Oh. Okay, so if we looked at that one is NC, which means what? Normally closed. So it's closed, like for a heating element of a dryer, and as it gets hot, what's it going to do? It's going to open to prevent it getting from too hot. Heater goes off, temperature starts going down, thermostat closes again, heater comes on, and it cycles the element on and off to keep an average temperature. Okay, so this one, is it open or closed?
Open.
It's open. Does it close when heat gets lower or when the heat gets higher? This one here, when it gets hot, it opens. This one here.
Get lower.
So when it gets colder, it closes?
Yeah.
Okay, so that's not correct.
It's not.
So, a good try though. You only had 2 tries. So when the hot air rises, it fills up this little hat. What's it gonna do? It's gonna push it up and then close the contact. So wait a minute though. If the thermostat open, is it gonna produce heat?
No, it's open. It's
So where would
The
we
contact.
use a normally open thermostat? It could be used in an area that has heat, but if it got too hot, it may close and turn a fan on to cool down. Like in a wall oven. In a wall oven, they got computer boards back there controlling the whole oven. But if you go into self-clean, you know, like these things have a cycle where you lock the door and all the grease gets burned up into ash. Okay? So that's good. It helps clean the oven. We don't need to use chemicals, but that temperature is 850 to almost 1,000 degrees in your oven when it self-cleans. So it turns all the grease to ash, and then just take a damp cloth when it's done and wipe it out. But you got computer controls above there that excessive heat could damage the controls. So a lot of those ovens have a fan up there, and if it got too hot, a thermostat would close, turn a cooling fan on to cool that area up, but during regular baking It doesn't get that hot, the fan may not run.
No,
Unless you're cooking like a turkey for 4 hours and that whole area is hot. So this is where we would use a normally open thermostat to turn on a fan to cool things down.
Okay.
So you see how we would use a part for a specific thing. What about this next one here? Oops. This one here is what?
It's an off and on switch.
It's another thermostat, but it has 3 terminals. You got
Single pole, dual.
1 wire coming in and 2 coming out. Single pole,
Dual.
double throw.
True.
That means it can go out here or there. Why would we use that?
If you want the heat to go out, that goes either way.
Well, if I want the heat to stop, I would put the heater here on the thermostat
And close it.
because then it would send power to the heater. And once it get hot, this thing's gonna rise. That hat means just like that. So it opens up, but then it closes to another circuit. Well, let's take a look at a dryer diagram for a second. And I had all these diagrams open. Don't tell me I closed them all. Okay, we're going to have to go back. I must have closed the Adobe program without even knowing it. 1 second, guys. I apologize.
What's up, Bo?
Where's my class machine diagrams?
Where's William? Where's William?
So let's take a look at. Let me see here. I'm just trying to find the I had all these diagrams open and I must have closed it by mistake. Looking for. I had a laundry center here. I think it was this one. Let me see. Is this it? Nope. Sorry, guys. I had everything open here before we got. Oh. Let's take a look at this dryer diagram for a second. Oh, this one don't have it. I know I had it on this diagram here. Here we go. So here we have 2 thermostats. One here and one here. It says NC, which means what?
Normally close.
So in this case, power goes to the heater, right? But that's not a single pole double throw. How would I use a single pole double throw unit? Well, if we look here, the timer circuit is right here and goes around here. So when this thermostat's closed, the timer won't run. Electricity is just going to go right past it. Once the thermostat opens, the timer motor is going to run. But in some dryers, and I had the diagram open, so I'm just going to have to just draw it for you. In some dryers, here you got power coming in. I'm just going to put the thermostat here. And then you got your heating element and goes out. But if I put another contact here, and I put the timer motor here, for example, right now the heater's on, right?
Mm-hmm.
What about the timer motor?
It's off.
It's off. So what would happen? The heater's starting to get hot, right? So as the heater gets hot, what happens?
It goes off. Goes
Okay.
the timer come on.
So this thermostat does this. When it gets hot enough,
It lifts up.
that will cause it to go up. And now it's going to send power here, and the timer will run.
Yeah.
Now this is one way they did what they call automatic dry, where like the heater was heating, but while the heater's heating, the timer's not moving. That other circuit I just showed you did the same thing, just different way, without using a single pole double throw thermostat.
So you use the double one. So when one goes,
One used for
So
2
while the
things.
heater's on, the timer's off. Now let's take a look real quick at a GE dryer diagram. I think I have one there too. No, that's the wrong folder. Here. GE dryer. I saw them, but this one here might be hard to read. Let's just see for a second. Now this one here is no good. I'll have to bring them out later when I'm done with the lecture here. Just see if something. Trying to find that double thermostat. I had it open. So we'll skip that and move on. I'll bring that up to you guys in the next lecture. So let's go back to I finished identifying these, for example. So let's just go one by one. Load or control?
Got just the one.
Okay, what does that mean?
You able manually to adjust it.
Okay, give me an example where I would find that kind of thermostat where the thermostat's adjustable.
AC?
Yeah, sort of, but
Dryer,
let's stick with the appliances.
dishwasher,
Sorry.
dryer, dishwasher.
Yeah.
Where in a dishwasher do you have an adjustable thermostat where you can adjust it?
Oh, I can adjust, or I gotta adjust with the water and thing.
Well, here, give an example. An oven.
Oh, yeah.
You got a selector switch, bake, broil, time bake, self-clean, whatever. And then you got a second dial that says 100, 250, 350, 500. That's your thermostat. And you can put it to 300, you can put it to 500. And that's what means adjustable. Now this thermostat is pretty much the same as this thermostat as far as one's normally open, one's normally closed. But the arrow at a 45-degree angle through any part means that part is adjustable. So back in the day, some Whirlpool dryers actually had an adjustable thermostat. They had a dial in the control and had a sensor went all the way down to the back of the airflow of the dryer. They only did it for a couple of years, but it's something they have it. Ovens, how about your refrigerator? Your refrigerator, you got a dial, you can rotate, right? But most of the other appliances, they may have heat or cooling, but most of them don't have an adjustment of temperature. They have thermostats in that cycle them on and off at a specific temperature, but not adjustable. So this is only used in specific applications. It's not used on everything that gets hot or
So would
cold.
that be used in a microwave?
Not an adjustable one. Most microwaves now are totally electronic, and they cook by time instead of by temperature.
So what about when they ask you high, low?
High-low is just the actual magnetron that's producing heat.
Okay.
On high, it's on 100% of the time. If I put it on anything less than high, the magnetron comes on, goes off. Comes on and goes off.
Okay.
But whenever it's on, it's full power. But when it's off, it's off. So it cycles on and off so it doesn't like overheat the food. Okay?
The same thing for a toaster.
Excuse me?
What about a toaster?
Well, a toaster's adjustable, right? You can make it more dark or light.
Yeah.
Yeah, it's adjustable. So what is this? Another thermostat, right?
Yeah.
Open or closed?
Close.
Closed. Put it over here. What's that?
Switch.
So it's a control or load?
Control.
Control. Single pole, double throw. It has 1 point in and 2 out. Another what? Switch. What's this?
A motor.
A motor?
Dual motor.
What about this?
Resistor.
Resistor or heating element. Another what?
Switch.
Over here.
Single.
A timer.
Timer motor. Okay? Timer has many parts. It has switches and a motor. So that's the actual motor of the timer. So that's a load. What about this?
No, a single speed.
It's a motor, like in a refrigerator, it has a little fan motor in the freezer or in the back of the condenser.
Right.
It's just on or off. It don't really have
It's a
very many
single speed,
speeds.
Yeah.
Yeah, so that's that. What about this?
Switch.
Thermostat? What about this?
Multi-switch.
Single pole, triple throw.
Yeah.
Multiple poles.
It's got 3 points. What about this?
That's a motor.
Where the heck did all that drawing
That's a
come from?
compressor.
Picasso.
Well, this one's not a compressor. This one's more like a compressor. That one is a multi-speed motor.
Okay.
That could be a 2 or 3 speed motor where they don't show the start winding, they just show the 3 run windings. So everything on this side is a load, and everything over there is a control. Can I connect any of them together? Like, can I just pick one part out and another part and put it over there? Like, let's just say I take this part and I put this thermostat here. Can I connect this thermostat to this motor like that? Can I connect them together? Would the motor run?
Yes, because when it goes on, when it touch, it send power to the motor.
Okay, so if I did this, that would be a complete circuit, right?
Yes.
Okay, a lot of times I see people when they're doing diagrams. I've been doing this for years, is where I tell you, use a single pole, single throw switch with a light bulb and draw the circuit, the complete circuit with it. And I get this. I get a, here we go. I get a single pole switch and I get a light bulb. And that's what I have students draw. Did they give me a switch?
No.
You gave you
No, they drew me a switch, right?
But,
Yeah, but it's not gonna.
Let's take it a piece at a time, yeah. Okay. Did they give me a switch?
Yeah.
Did they give me a light bulb?
Yes.
Did they complete a circuit?
No.
What is wrong?
The light, the switch is on.
Oh, the switch is
I
off?
mean, it's off.
But the wire's
Okay.
not connected.
And then the wire's not connected to the other.
No,
light.
continuity.
So what do I need to do?
Draw
Put
a
in
line.
continuity.
Turn the switch on,
No, down,
down.
Oh, okay, so what do you mean by down?
to the close,
To the table.
Come on.
to the, right.
To conduct.
You still got.
Well,
And
you don't have to draw the switch closed, because in some diagrams, the switch is drawn
It's
open. You just have to know when the customer turns the machine on or manually turns that switch, that then that switch is going to close.
Yeah.
But knowing the circuit, and what I mean by that is like when people do this, I've seen them take this second line and put it over here, or put it way over here, like not even like where the switch is, and making it part of the switch, because they see it go like this and they see it like this, and they don't realize that when the switch closes, this piece actually touches right here. And that's how power goes through. But a lot of people look at diagrams and they don't understand that. So that's why I'm doing this, is why I'm breaking it down, like these are how these parts work. So I'm gonna pick 2 parts. Hold on a second now. I'm gonna pick 2 parts. I'm gonna pick a thermostat here. What would a thermostat be connected to?
Heating element.
Okay, so where's my heating element here?
The second and the
The
first.
Zillion line.
Second.
The second one?
Second low in the.
Yeah.
What is it?
Right here.
So I need these 2 parts, right?
Yeah.
So if I go like this, and I copy. And I bring them over here. I'm gonna put this one in here, and I'll just make it a little bit smaller to fit in there. And then I'm gonna put this one here. Is that a good circuit?
Yeah.
I mean, I know that the white part is keeping it from drawing the line, but that would work, right?
Yeah.
Okay.
L1, L2.
What if I did this? Oops.
It works still when it's on and off.
So it doesn't matter if the control is in front of the load or not?
No.
They need to be in serial.
It just letting you know that the heating element ain't got straight power to it, and nothing, they're gonna turn it off or on till it goes a little further. And
So if there's no switch here, there's power at this element all the time?
yes,
Yes,
Is it getting hot?
no.
yeah, yes.
If it's not connected to
If
the
it's not
outside.
connected, yeah,
The
If
switch
it's
is
not
open.
connected, let's just say this thermostat's not there.
it's not getting hot.
It's got power though, right?
It's gonna probably
It
get
got
hot, but
power
not as hot.
yeah, no, cause it's not going to the negative, it's not going to
Okay,
the
well, hold on a
negative.
second now.
No, it's not gonna get hot.
It's not getting hot.
No, because it needs to connect to.
So power come, I didn't want the black one, I wanted a different color. So power,
Cut it out.
Take green. Yeah.
so power came in here and it stopped there.
Yeah,
Is the element getting hot?
No,
no,
The bottom tilt is alright, Professor.
But I have voltage, why isn't it getting hot then?
because there's no connection to take the voltage out.
If there's no connection, what is not happening in the circuit?
It's not rotating it back around.
How do we say that in,
I don't know how to say it. I know
well,
what
do you
you're
guys
saying.
know what he's
Is it
saying?
rotate?
yes, I know what you're saying.
Well, so what's, explain it to me.
I don't know how to do it.
That's okay if you don't know, there's someone gotta know.
Say it's not rotate.
But,
It's not,
It's not
the current is not, rotating.
There's
back
no
and
current
forth.
flow.
There's
No
no current
current
flow,
flow,
yeah.
back-
Okay, so as soon as you plug it in, electricity's over here, line one, neutral's over here. So electricity wants to go in line one, come out neutral,
Yeah,
okay?
That's right.
It's gonna go in and come in here, and it
neutral.
will flow through the element till it gets to here. You know how fast it takes to get from here to here? Like that.
yeah.
As you're plugging it in, before you even let go of the plug, the electricity already made it over to here.
And it's not going to.
But then it stopped.
Yeah.
Unless the current is continuing to flow, there is no heat being generated by the element. Okay? So let's clear these parts off. Alright, let me move these two. Let's pick two more parts. Okay, I want to put, let's put a light bulb. What am I going to put the light bulb with?
Switch.
You can put
Okay,
it,
pick a switch.
you can put any switch. You can put a single pole switch
A double-
or a double pole switch.
Well, from the top down, tell me which one do you want? One,
Just a
two,
switch.
3, 4, 5.
The single pole one.
One at the bottom, the one at the bottom.
This one on the bottom here.
Yes, yeah.
So I'm gonna take these two,
Boom.
and then copy it and paste it into the other diagram.
Matter of fact, you can probably get a three-speed motor and put it on there.
Well, we're gonna start something simple. Would that work?
Yeah.
Okay, what if I swap the switch and the light? It would still work,
It
right?
still work.
Okay, so you have to understand by the way I'm putting them in there, that this is just a place for power to flow through the whole circuit. And when we're troubleshooting, everything has to do with voltage, everything has to do with power, okay? All these loads need voltage to work. All the loads need voltage to work. Always remember that, because if you're going to work on an appliance, 9 out of 10 times, there's something wrong with the appliance that's specific to one function of the appliance. What I mean like that is a washing machine. The customer may just call out and say, I have no hot water coming in, or I have no cold water coming in. Or it fills up with water, but it don't wash. Or it fills up with water and washes, but it don't drain. Every one of those things I just said is only one function or one part of the machine. Now, when I tell you the machine fills up with water and washes and doesn't drain, to a customer, that's all they know.
Yeah.
As a technician, when I say it doesn't drain, what am I telling you as a technician?
They look for this, where go to the diagram and find out where it starts, where the switch, come on.
Okay, but if I'm saying not drain, I'm talking about a specific part, aren't I?
Yeah,
The motor.
Drain pump.
That-
Drain
Yeah.
pump?
Or it could be the main motor on the direct drive Whirlpool washer, the main motor, the pump's attached to it.
Yeah,
Okay, but see what I'm saying is like, your troubleshooting of an appliance begins the moment you talk to a customer. It doesn't begin the moment you start looking at the diagram and start taking parts off. You as a technician, you go into your office, or let's say it's your own company, and you have a certain amount of customers to do that day. You're gonna look at Ms. Jones, the first customer, and it's gonna say washer does not drain. Well, immediately in my head, wheels start turning saying, okay, it don't drain. The drain pump may not be working, so the problem may be with my drain pump.
yeah, she already did the job for you.
Oh, the switch.
But what else in the machine could stop the drain pump from working?
A switch.
It's
A
close.
switch?
The leveler,
Clock.
A control board?
yes.
What about a lid switch?
The
If
door
the
switch
lid
down.
switch is broke, it may wash. On some of the lid switch is only good for drain and spin because we don't want to spin and the customer look at that lid. So some machines will wash but will not spin. So now it comes down to machine specific. And this is one of the reasons why when you guys are working on the machine, first thing I say is hook it up, run it through a cycle. You know, a lot of you still, and some of you are ready to graduate, turn a machine on and couldn't tell me step by step what that machine does. But I could walk up to the machine and you have the machine running. I say, oh, that's not working. I just walked up, I wasn't even there for 30 seconds and I already know what's not working. Okay? You guys, when you're working on a machine, have to know, washer don't drain. Okay, it could be a drain pump or it could be anything that tells the drain pump to work. Okay, now I want to look at the diagram and see how does the drain pump get power and all the switches that are controlling it, because if the pump's good, that switch could be bad. Those are the things I need to check when I'm troubleshooting the dryer.
So when you read the
Or
pump,
the washer,
you
whatever.
read it in ohms or, you read the pump in ohms?
What did I just say a minute ago? Every load needs what?
Voltage.
Voltage. So if you can safely check voltage to the load, that's the first thing you need to do. Now, that's if the machine is working, but a part of it is not working, I'm gonna go right to the load. But if the customer calls you and says, my machine's not turning on at all, well, before I take anything apart, I'm just gonna check to see if there's power in the outlet in the wall.
Outlet, yeah.
Okay? But going back to this, troubleshooting begins with the steps of, okay, what's the complaint? What parts could cause that problem? What do I test? Now I go to the diagram and see the circuit of how that thing flows. All right? These are the steps at which we have to troubleshoot. And it all comes down to, I need to know what a machine's doing when it's running. I need to know the sounds. When I'm talking to a customer, without even thinking now, I hear machines running. Like, I hear that ice machine cycle all day long. Okay, it's running right now. You probably can barely hear it. I can hear it running. I hear the compressor and the fans running and the water circulating. Let me just see something.
It's filling up, it's
I
nice.
can't hear it. He has a good ear. I
listen.
can't hear it.
No, my hearing sucks.
I can't hear it, man. Mine was worse.
Can you hear the water?
Yeah, it's
I
filling
don't
up.
hear it.
No, it's circulating the water. It's making ice.
Y'all probably just filled up.
It's already full, but it's just constantly circulating. But the thing is while I'm talking to you tonight, I'll hear it cycle and go to drop ice at every step it makes. But I know every one of those sounds. I'm not asking you guys as students in a school to memorize and know every sound, because that's only going to come in
Due
repetition
Due
and
time.
constantly do it. Just like muscle memory. My brain is a muscle. Muscle memory. You know, your brain, muscle memory. You have to be familiar with these sounds, because that's the first thing. You know, you hear something wrong, you're going to go right to that to try to figure out where my problem's at. Let's do another thing here. I'm going to switch it up. I'm going to ask one of you guys to come up here. So I'm going to say, I'm gonna take this one, let me move this out of the way, this one, and this one. We'll take these three parts. Okay. Now, this diagram can't handle all three of those parts, can it?
No.
Well,
Yeah,
the way
you
that
can.
switch is designed,
You can.
the way the switch is designed,
You can have one
it's
go up.
closed in one way or the other, right? So I want someone to come up here and hook it up, and they're gonna have to add some wires now. So I want the germicidal lamp to come on first, and then when it goes off, I want it to turn on the incandescent lamp. Who wants to do it?
No, I do it.
He jumped out before you saw it. I'm sorry, he was rolling on the seat. Okay, so add them. Where do you think they would go in the circuit?
The incandescent first?
That one go there first. Gotta add wires, so you want that one to come on first.
No, I want the germicidal to come on first, the incandescent. Let's make them a little bit smaller so they can fit on the diagram. Oops. I should have made them transparent, but. Right.
No, this one in here. So it'll go. I'm trying to draw a line.
I'm gonna take this diagram piece out, and then you draw your own diagram.
Okay. Go ahead.
No, you have to click on the pencil here. Go ahead.
Oh, you wanna go up, gonna go right here, go down.
That's not correct. Anybody want to come in?
I don't know.
Let Paul see if he can correct it. But before you correct it, explain to me the way it's drawn.
If he goes up here, this will turn this on also.
In series.
Yes. We'll turn it
Okay,
on.
but actually the way he has it, in this position, that light will come on, that won't.
Right.
But then when it goes up here, then both will come on, right?
Okay,
But
I see
here's,
what I did.
here's another thing that I wanna show you. Let me just clear the drawing altogether. That he had, like the line going like right like that through the two dots.
Yeah, well,
It's not 100% wrong, but that's not the way electricity travels. Because if you put a wire like that, the electricity would just go right past the light bulb. When we do it, we're gonna run one wire in and one wire out, so it goes through the light bulb and back out like that. Does that make sense?
yes, that's what I mean.
I understand, but other people are looking at it and they might not understand. I know where you're coming from, but some other people might not see that. So, Paul, here's your three parts. First is the arrow, so you can move where you want. I want the
Incandescent.
the germicidal to come on first in our drawing. So, here's pencil, or if you want to move it, you gotta click the arrow.
In this position, this is first, right? This position is first.
Yes.
Yeah, okay. But we're put a thing right here.
That's to draw, yes.
Yeah.
Let's change color then. Go ahead.
I want to move this.
Okay, so then we click on the arrow. Go ahead, move them wherever you want to move them.
No, with that switch, it don't matter if it's up or down for on. It can
Well,
turn
one will
on
go on and one is off.
One to go up when it goes up, okay.
Yeah. Yeah. Good. Good.
Now, that will work just fine. So, the way he's got it drawn is that power come into the switch. In the bottom position, that's lights on, and the top position, lights off. I would only do it a little different as far as it's drawn right. I would just make it a little bit tighter diagram, make it look a little bit cleaner, because what happens is it looks like everything's too far away. So I would do it like this. In, I'm gonna come out and go like this, and like this. And put this light here, and I'll put this light here, and then I just go like this. Try to keep it in nice, straight lines. You're not gonna draw diagrams every day. Now, I've said this story before in some of my videos and everything else. Straight out of school, I was 17. I graduated in high school appliance. I went to work for Sears. They had a slide-in range. What a slide-in range is, it doesn't have side panels because they go in the cabinet and they hang or they sit inside the cabinet, so they don't need sides. And I got a part, I had a box with a thermostat for the oven, and I knock on the door, and lady opens up the door. I say, "Hello, Sears, I'm here to fix your stove." She says, "What do you got in the box?" And I said, "It's a thermostat. A technician came out and ordered the thermostat." She says, "That's the second one. This stove's a month old. I don't want this stove anymore. I want a new stove." I said, "Ma'am, you know, if you want to get a new stove, you need to go to the store, but I'm here. Let me see if I can fix it for you." She says, "Well, every time they put that thermostat in, it blows up. Brand new machine, blows up." "Well, ma'am, let me check it out." I go over there. Sure enough, the thermostat was bad. And the thermostat had, I don't know, 5, 6, 7 wires on it. And then it had a selector switch, big broil. This wasn't a computerized machine. Now, we're talking 1983, okay?
Yeah.
So I said to myself, well, brand new stove, this thermostat blew up. Either something inside the oven is shorted, or maybe they put the wires on one of the switches wrong, and that's what caused a direct short. So I lift up the top. Right there inside, underneath the burners, is the diagram glued to the machine. Okay? So I look at the selector switch and I says, oh, blue goes on number 2, orange on number 3, blue on... The diagram don't have a blue wire. But this machine has a blue wire going to this switch. I'm looking at the diagram at the switch. There's no blue wire.
Excellent.
Manufacturer glued the wrong diagram inside the machine. What am I going to do? Because this lady's already upset.
She's already hot.
Okay? She wants a new stove. I already blew up the thermostat I put in there. Turns out the thermostat only blows on the self-clean cycle. So what do you do with that information? What's our next step before I tell you what I did?
Self-clean circles.
I'm sorry?
No, you said self-clean circle. If it's
Self-clean
cleaning itself.
cycle. That's where I put it on bake, it worked. I put it in broil, worked. As soon as I put it in self-clean, boom, blew up the
highest
thermostat.
it get. So y'all look at the thermostat.
Maybe they look
Thermostat's what blew up.
Oh, that what blowed up, then I'll call my supervisor. You at work?
No, okay, yes.
Maybe see which contacts are used in that circuit for.
That's my man.
Yeah.
Good job, bro.
Yeah.
You go to the diagram and you look at the self-clean circuit for the diagram, and we're gonna look at all those switches in the diagram. Well, guess what? That blue wire's in that circuit. Guess what? The diagram don't show that blue wire. Now what?
The blue eye was extra. Was it extra?
No, the diagram that the manufacturer glued to the machine
Or was it one?
glued the wrong diagram.
Okay, the one.
Now, let's go back. This is 1983. If you guys needed a diagram, what would you do right now?
Down.
Go on the internet. In 1983, where was the internet?
The catalog books.
No.
When it was between
When I told
service.
my boss that the diagram was there, oh, we have to call the factory. They can fax us over one
No.
or mail us a diagram.
No.
I was like, huh? Well, before I left the house, I was like, okay. So if the diagram's wrong, I need to make my own diagram. I took the selector switch, put it on bake, and I touched every terminal. Which ones are giving me readings? Oh, 1 to 3 and 1 to 5 in bake, okay? 1 to 3 and 1 to 2 in broil. In clean, it was 2 to 3 and this and that. And I made my own chart, what switches were closed in what cycle. Then I went to the thermostat, what switches in the thermostat are supposed to be closed. And the thermostat was almost like the one on the diagram, so I could use part of the diagram to give me an idea where the wires go. But again, there was wires in the machine that didn't match the diagram. So I drew an entire diagram of that oven and rewired it the way I think it should go. I go back to the office at the end of the day. My boss's name was Mr. Barry Newberg. Hopefully he's still around. Remember I was 17. He must have been in his late 20s, early 30s. So, he's definitely a lot older than I was. So I came to him and said, hey, Mr. Newberg, there's a wrong diagram on the machine, but I drew this diagram. He said, hold up. You drew this? Yeah. I'm thinking to myself, what's the big deal? But 90% of the guys in the shop can't do that. They weren't formally trained like you guys are in school being formally trained. They can't do this. So he says, well, I'll call the factory. And he takes and he pins it up to the board he had behind his desk just because he couldn't believe I drew this diagram. I'm a 17-year-old kid. There's guys 30, 40 years old that have been with the company 10, 20 years that can't do that.
Yeah.
I was one of the few people they sent behind those guys when they couldn't troubleshoot the machine. Not that I was that much better than them, but I had training they didn't have. So anyways, the very next day, I was sent to the Keys twice a week to do service. So next day, I'm going to the Keys, and I'm driving down US 1, and in the back of my head, man, I got to wait for thermostat, and I need to get the diagram, and what else could it be, because I still didn't find exactly. I needed to order a thermostat again for the third time, and got the customer to give me one more try. Okay, because she could use the oven, she just couldn't self-clean. So I said, ma'am, just give me one more try to fix it. So as I'm coming back from the Keys, going up US 1, Cutler Ridge Mall, if you guys know where Cutler Ridge is, down off US 1 and Turnpike, had a Sears store. And I'm thinking, wait a minute, she bought this stove a month ago. There might be another stove just like it in the floor.
Oh, done it, Home Depot.
Mm-hmm.
Well, we didn't even have Home Depot. It just came out back in the 80s.
No, I'm saying I would have went to another Sears store and just got the.
But that's what I'm telling you is, I'm coming up US 1 and thinking that same model was in the store. I drive into the store. I'm wearing my Sears uniform. I walk in. The salesman guy, help you? No, don't worry about it. I know what I'm doing. I go up to a stove, act like I own the place. I lift up the top of the stove. No diagram. The one that I was working on, it was glued down. So I look, and there's a little pouch in the back that had the diagram in the pouch. I open it up, and ta-da, little, like the lights come on, ta-da. So I take the diagram, and he goes, where are you going with that? I said, I'm going to make a copy. And I went in the back of the store, made a couple of copies, put the original back in the floor model, go back to the office and say, hey, Mr. Newberg, I got the diagram. He's thinking, I said, where'd you get the diagram? I said, I went to the store and found the same model on the floor and took a copy of it. He surprised, there's this 17-year-old kid drawing these diagrams, going to get he didn't think about that. He's the supervisor, right? So I drew the diagram. He took it and took the diagram I drew, put them side by side. My diagram was identical, except I had two wires backwards, but they were the same two wires like here. If I switch them this way, it really don't make a difference. It was only two terminals, and if you put them the other way, it didn't matter. But that was the only thing I had wrong, and I wired the stove up right just by my own drawings of the diagram. Now, you guys almost will never, ever have to do it. But just the other day, you guys were working on a GE dishwasher. There was no diagram in it. Without a diagram, it's even hard for me to troubleshoot something if I don't know what the part is and how that part works and when that part turns on and how much voltage do I get to the part. So reading these diagrams and knowing and understanding how these diagrams work is how you're going to troubleshoot this appliance. Every time you touch a machine, I don't want you testing parts without looking at the diagram. And even if you're just looking at it, say, that's the part I'm testing, that's it. Because this is what's going to make you better at diagrams, looking at them every day. You can't just spend 1 day a week studying diagrams. You can't sit at the table just drawing diagrams all day. You need to take the diagram and put it to the machine and see a part in the machine and find that same part in the diagram and see how that part is in the circuit of the diagram and what parts turn that on and turn it off and how they turn it on and off. This is troubleshooting. So let's try a different diagram. Let's see here. What's this part right here?
Resistant.
It's a coil. What is a coil?
Like a transformer.
It could be a transformer. What is a coil? When I give it power,
It's a magnet.
it's a magnet. It's an electrical magnet. That's what's inside of your water valve. Thought I had one sitting right here on my desk. It's been moved. But a water valve in a washing machine is a magnetic coil. So, what am I going to connect this with? Am I just going to use a regular switch? Am I going to use a thermostat? What am I going to use? What would normally you think would be in series with that? A thermostat? Thermostats usually are in series with what?
You need a,
Heating
you
elements.
need a switch.
Or the opposite, cooling components. But if we're trying to control temperature, that's where we're going to find thermostats. So we're just going to have a regular switch or mechanical switch controlling it here, right?
Yeah.
But what if I want to put a thermostat? Let's say that magnetic coil opens a door that lets warm air in. Now, if it's too warm, we want it to close back up, or vice versa, right?
Take the adjustable one.
Well, we'll add an adjustable thermostat to it,
Yeah.
okay? So I'm going to take these 3 parts. And who's my next person coming up? I want power to come in through the main switch, go through the solenoid, then the thermostat on the other side, and go back out. Someone draw me the whole diagram and put those parts together. Who's coming up? Why are you looking at Francois?
No, I'm just looking at the machines.
Come on, someone want to give it a try? Nobody? Okay, so I want power to go through the switch, into here, and then there, and out. So you gotta draw the whole diagram.
Okay.
So you need the arrow if you're gonna move them,
Okay.
or the pencil if you're gonna draw, okay? Now, I want nice straight lines, so make everything nice, clean, and organized so everybody can see what it is you're doing. They're a little too close together.
No, I'm just making my lines. I'm gonna move it. as I
Okay, go ahead.
What do you want first, Professor?
Is it
He did it, that switch.
To the switch.
You wanted to go through
To the coil.
We need to draw a line now.
Yeah, right here.
To the coil. The switch. And just to
And what you said again?
And then the switch.
And this switch?
And you draw another line.
Mm-hmm.
Now add the switch, and then draw another line. Okay, thank you. It's perfect. Just connect it, that's all. How many wires are in this diagram? Like, and when I say that, I mean like, if you were to open up the appliance and it had just this inside of it, how many wires would be used to make all those connections?
I would say one.
4.
Okay, you count, each
One,
line dot.
2, 3, 4.
Oh, so you count each dot.
Well,
Why?
that is a wire connecting this to this. That
Okay,
is a
gotcha.
wire connecting this to this. That is a wire going back to the plug. That is a wire going back to the other side of the plug.
And if you wanna test, you test every portion, right?
Well, let's talk a little bit about that. Okay. If you want to test what?
If you wanna test the components.
Okay.
Or the parts. you-
Test them how?
With the multimeter,
Okay, am I testing ohms or am I testing voltage?
voltage,
Okay.
or continuity.
So, what? One or the other though? Which one are
In
we
this
talking
case,
about?
voltage.
Okay, so what am I gonna do?
I will test the switch if it's failing, or the coil.
But you're gonna check the switch? How are you gonna check the switch? With voltage?
I will check if it's, I need to know if it's, current going to the switch first,
So how are you gonna check it?
with the multimeter.
So these are the only
I
two
go
points.
from
These are the only 2 points on the switch. There's 2 wires connected there.
Yeah,
So if I put my meter here and here, and my meter says 120 volts, what does that mean?
It doesn't mean that power going through it, you still gotta, connect, from the power. And here, to see if it, when it connect, it works.
but, in that case, the switch is open, I will have that reading.
That's the only time you're gonna get a voltage reading if the switch is open.
Okay.
That if this switch was closed, like this is line 1 and this is line 1, your meter is gonna say 0 volts,
Okay,
okay? But when the switch is open, when the switch is open, you have line 1 stops here, neutral feeds back through all these parts. If I have 120 volts here,
yeah,
that means everything else is good. Because if that switch was bad, I won't get a voltage reading. If this coil was bad, I won't get a voltage reading. If this switch was closed, I won't get a voltage reading.
okay.
But that is not a good test. We do not like to check switches with voltage. Because I said that if the switch is open, I get how much?
120.
If the switch is closed, how much do I get?
0.
0. Okay, so if I get 0, does that mean my switch is good?
No,
Why not?
no, I know.
I said if it's
no
open, I
problem.
got 120. If it's
no
0,
problem, because
It is
it's
good.
continuity.
Continuity.
okay, but wait a minute. Let me ask you a question.
It's gonna
Hold on, hold on. Let me ask you a question, and you can say it. If this wire's broken, what voltage reading would I have there?
Zero.
0. But now you're telling me my switch is good because I got 0 volts.
But no, I was gonna say,
Voltage is not good in that type of test. Okay, so let's talk a little bit about voltage and voltage testing. Now this is just the beginning because we're going to start having more and more lectures on diagrams.
Yeah.
And I have assignments for you guys to do, almost like the assignment where we were drawing and putting these switches together. I'm going to have you guys do some of them. We're going to get real complicated with some of them, to where you guys are reading some real crazy diagrams. But when we check voltage, there's 2 main parts we're going to check voltage. Where are the 2 main parts on this diagram I would do a voltage test?
I'll do it at the plug.
Okay, the plug would be here. So I put a meter here and a meter here for volts.
Yes.
I have 120 volts. What does that mean?
The circuit
I got
is
power.
full.
Means the outlet on the wall, because that's where they go. That means the wall has voltage. Okay? Where's the second place you would check voltage?
In a motor?
We don't have a motor here.
No, okay, right there. Sorry about that.
We're talking about this diagram. Where would you put your meter? Yes, sir.
I'll put the meter, where the line, the second wire go to. No.
One second. Let me finish his thought.
I'll put it, just go.
Okay, what were you going to say, Francois?
Maybe L1 at the beginning of the switch, and then
So you're saying here?
Yes,
Okay.
and but doesn't it depend on what we're testing for?
This is not working. This could be bad, this could be bad, this could be bad. Any one of them wires could be broke, right?
And I can try again.
Okay.
Would you
Alright,
check?
what I would do.
Wait, before you say it, let me just add something and then you can say what you want to say. What do I have here?
120.
Where do I need it in this circuit?
Line 1.
No. Where do I need it
At
in this
the
circuit?
element.
Not the element. It's not an element.
I mean,
If you don't call it the right part, I'm not gonna give you credit.
Yes.
You need to learn these parts.
The core.
The coil.
Yeah.
Where on the coil?
The core, I'm sorry.
Where on the coil?
At the 2 points,
Okay, so if I put a voltmeter here and here,
yes.
and I get 120 volts here and here,
That means the core is
core is good.
connected and the power going through it.
okay, not going through it.
I mean,
That means power is going to it. Now, let me explain something. There are many different tests we can make. We can make an ohms test, a voltage test, an amperage test, a wattage test. But as a technician, the two main tests we're going to use is volts and ohms. All right? Voltage checks for electricity, for power. We check to see if we got power in the wall, because if there's no power in the outlet, you can plug in anything you want in there, it's never going to work. Okay? If you have voltage, the next thing you want is I want that voltage to get to the load. The load. Everything else just sends power to it or turns power away. That's it. Now, when I get 120 volts, what am I actually checking? Am I checking the coil?
No.
What am I checking?
Checking to see if electricity
If
flows.
the circuit is continuous.
I'm checking that this circuit is good here and this circuit is good here. If I have 120, everything I just drew a red line on, a dread light, everything I drew a red line on
Electrical flows.
is good.
Yes.
So in this case, what is wrong? The coil is
The
bad.
coil.
By having voltage at the coil and the coil still not working, the coil is my fault. Because that's what the rest of the circuit does, is take the power from here and put it there. And if my meter tells me it's there and it's still not working, I don't need to test anymore. But my test is not checking the coil, my test is checking the circuit that provides power to that coil. And that's what we're checking. If I have voltage there, that means the only thing left, it's bad. But if my meter says 0 volts, what does that mean? I have 120 here, but I have 0 at my
I
part.
mean, one of your switches is bad.
Bad.
Or could it be a wire?
Yes.
So what's my next test?
Now we take a look at the switches and you check the switches individual with the ohms.
Okay, let's say I put an ohm meter here and I get 0 ohms. What does that mean?
That means it's working when it touch on.
The switch is closed.
Yes.
That's good. I put my meter here, I got 0 ohms. What does that mean?
It's making contact.
But I don't have voltage here.
That mean your resistor is bad.
No,
Oh, the switch.
I don't have voltage here, but I ohm this out and it says the switch is closed, and I ohm this out and it says the switch is closed. That means both of them are good, but I still don't have electricity here. So that means one of my wires are broke.
Yeah, something wrong.
But that is not a good test. Going from voltage, now all of a sudden switching to ohms is not a good test.
So you gotta stay in voltage when you do
We're
it.
going to stay in voltage as long as we can stay in voltage, and we can do it safely when we're not going to electrocute ourselves or somebody else. Okay? But-
Let me ask you, how can you stay in voltage if you're gonna check?
I'm going to show you right now.
Okay.
Let me just try to race without racing on lines. So, you're here, 120, you go here is 0 volts.
Right.
So, in a machine, these parts are all in different places of the machines and they're connected by wires going through the whole machine. Okay? So there's a wire in the back of the machine that goes to the switch, let's say a door switch, and from the door switch it runs to the water valve, and from the water valve it goes to a thermostat, and the thermostat goes out. Alright, so if I have 0 volts here, this could be bad, right? This could be bad, or any one of my wires could be bad. So if I have multiple parts on either side of my load, I want to know which side is my problem. So what I do is I take 1 meter lead and I remove it from the solenoid. I leave this one on there. And I take this other meter lead and I go all the way over here. So
You bypass it?
from here and here I had 0 volts, right?
Yeah.
But I brought this one to the neutral side of the plug, and all of a sudden I have 120 where when here and here I had 0.
So you bypass
You
it.
bypass the switch?
Now, I didn't bypass, I just wanted to see from here and here, do I have voltage?
Why?
What does that
That
mean?
means the left
Broken
side
wire.
is good.
Ah, there you go. That means
side.
that everything on this side's good. My problem is on this side.
So that means we're gonna rig it up and bypass it.
No. Now, just remember, I haven't signed your certificate yet. Okay, so I go over here and I find voltage. So I say, okay, now I know my problem. So then I'm gonna bring my meter leads back to here, and I'm gonna take this meter lead here, this one, and I'm gonna move it. Let me just erase it again, dang it. I'm gonna take this meter lead here, and I'm going to move it here.
Now you testing it. You
What am I
breaking down-
checking?
You breaking down the
Your
wire.
line.
Okay,
Your line.
okay, so this is what it is. If I have 0 volts here, but all of a sudden I get 120 here, what does that mean?
That means your wire is bad.
That wire's bad.
Yeah.
But that's not how we look at it. Because if I have voltage, voltage is telling me what's good. And I know that it's voltage from here to here,
So you
but I don't have it here, so now I know the wire's broke.
You're gonna move your lead over to that one. and
Now,
check
if it still said 0 volts, the next step would be to take this little red wire here and move it to this side. Oh, I have voltage here, but I didn't have it here. It's going in the thermostat, but it's not coming out the thermostat. My thermostat's the problem. So we started,
it. Oh, you start eliminating the part.
we go in here and one by one, we're backtracking to find where we have voltage, where we lost it. I don't have voltage, I don't have voltage, I have voltage. Okay, it made it this far, it didn't make it to here. My problem is that part. Does that make sense?
Yes. So if I wanted to just check the outlet with the 120, I got power coming in, but now I want to switch to my meter to the ohm. Can I do that same step with the ohm test?
Well, you don't want to backtrack with ohms. What ohms now is you're like, okay, I want to check the coil for ohms, I want to check the switch for ohms, I want to check this for ohms. But what you could do, let me eliminate all these lines. for a second.
Use continuity.
Well, let's say, yeah. But what I could do if I want to do ohms, remember I went here to here for voltage and I had it, but I didn't have it here, so I knew that was my problem. I could also do an ohms test, but I'll take 1 ohm meter and put it here, and 1 ohm meter over here, and my meter's gonna say, oh, you don't have a reading. And then I'll just backtrack. Oh, I don't have a reading? Do I have a reading here? No, I still don't have a reading. Do I have a reading here? Oh yeah, I have a reading, so this is good. I don't have an ohms reading here, so I could do ohms that way too, right?
Yes.
Let's take a look at a diagram for a second. No, not this folder. Here. I'm trying to find something with a computer board on it. Give me 1 second here. This is a Frigidaire stove. You got your bacon broiling it here. Okay, got a control board here that turns the oven on. We have a lock motor that, like when we go to self-clean, that locks the door. We have some switches, and we have a thermistor and a lamp, right? So, if I put my meter lead, you know what, let me copy it and put it in the diagram where I can draw it. Give me a second here. Have to make it fit. If I want to check that switch for ohms, can I check it from the control board?
Yes.
The lock switch, how do I check the lock switch?
You gotta go up to the dot.
Check the line. That
You
take
gotta
you
follow
to
the
the,
line, you gotta follow where the line go, where it goes in at.
on the control board.
Okay,
On the control.
I'm the technician in the house, I don't know how to check it, I'm calling you as a technical support. And I need to check that switch, where do I put my meter to check it? How do you tell me, where do I put my meter, specifically? This point is where I want you to do it.
Go to,
Line
L1
five.
of the switch.
L1,
Well, the L1 to where the switch at.
Line
the
five.
switch comes off the board.
Okay, so what we're gonna do is, okay, I see the letters on the board, okay,
Easy.
Yes, Francois?
I was gonna say maybe open the circuit board, look for 15, the wiring harness, and then,
Why 15?
cause that's what it's labeled as, the port where
That's what it was.
The connector?
the connector.
The connector's not called 15. Cause there's a number 1 on the other end of it, right?
call
Oh, yeah, I didn't see
So what's the number 1 and the number 15?
line
the
one.
number of ports,
Pins.
pins.
Pins are connectors on the board. If you count, starting right to left, pin 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
Number
This
9.
has the ability for 15 wires to be connected, but we got this big long plug, but there's no wires here, there's no wires here, and there's no wires there.
Number 9.
Just number 9?
Bueno, it's one line to the
9 and 10.
9 and
9 and 10.
Yeah.
Then if I put my meter lead on pin 9 and 10, that'll go like this and check.
So
Like switch.
you always count from right to left, or you count?
Well, no, because it has a number 1 and a number 15.
Oh,
They're
okay,
telling me that pin is number 1 on the board.
Okay, gotcha.
And diagrams tell you that, but sometimes this is actually drawn the way you would look at it on the board. You would see these wires on the side going to the elements, and you'd see this section here connected to the board, and we'd look at it. Let's just look at one more diagram with a board on it.
Would you do voltage or ohms on that?
I would ohm out that switch. I think I had a refrigerator diagram here. Just give me a second to find it. I don't know if this is a computerized one or not. Here we go. Now, when you got bigger boards with a lot more connections, you have all these letters and numbers. And like that stove, number 1 through 15 was right there. They're all in the same place. In this case, they don't put all the pins right next to each other. But they tell you the plug is J3 or jumper 3 they call it. The plug is J3, but the pin on that plug is pin 1, 2, 3, or 4. But this is J2. Okay? But look, you got a J2 8 up here, J7, J11, J7. So you got 7s here and 7s there. So they're not physically drawn all right next to each other, but J7, every one of these wires are all on the same connector. But if you notice, this is connector number 2 and number 3, but this is number 11. Okay? Now you're like, well, when I look at the plug, how do I know which one's pin number 1? Well, a lot of times on the actual board, and I want you guys when you're working on the machines to look at the computer board and see the connectors on the board and see if you can find a marking number 1 on all those connectors, that which one is pin 1, then you know the rest are 2, 3, 4, 5, 6, 7, 8 after that. Okay? If you don't know which is pin 1, because sometimes the number 1's not printed on the board, I could look at, where's J71? Is this one, what color wire is that?
Black and white.
Black with white, because J79 is orange. So I look at the plug, and I look at all the wires on there, and if it's number 1, it's on the end, one or the other. I'm going to look for a black wire with white on it, and that's how I know, okay, that's number 1, so the next one's 2, 3, 4. Oh, there's no wire on 5, but 6, 7 there are. That's how I figure out where my connectors are on the board. Now, I went way too far from what I wanted to do as far as like simple, basic, to something more complicated. But tomorrow I'm going to give you guys an assignment, which is drawing diagrams. I'm not giving you the symbols. I'm going to tell you, put a single pole, single throw switch connected to 2 light bulbs in series. And you have to draw it.
Okay.
You can use your basic electricity books for the symbols and how they do it in the diagram, but I'm not going to give you answers to it. We'll go over it in the lecture. Not tomorrow. We won't go over it tomorrow, but I'm going to give you the assignment tomorrow. Okay. Any questions on what we covered for today? I'm going to stop here because we got a lot more to do, but we're going to build on what we started. Yes, sir.
The example that you put with the heating, with the coil and the thermostat, like 2 diagrams ago, I've seen some diagrams where the thermostat will be underneath maybe the coil, and they're supposed to interact with each other in a certain way. Maybe not the coil, but like a heater. Maybe I'm confusing it with a heater or a resistor, but they'll put the thermostat underneath, and it's for a specific reason.
What did I just draw there?
Parallel.
What is that?
The switch,
What is that? Starts with an
It's a
R.
link.
Starts with an R. No, the dotted line means mechanically linked.
relay.
It's a relay.
Yeah.
So when power comes through here, the coil, what happens to the coil when we give it power? It becomes what? Magnet. And the dotted line means that this is part of this. It's all one part. And the switch gets pulled up by the magnet. And then when the thermostat says it's hot, opens up, coil loses power, switch opens, light goes off. Okay, so what you were probably saying is something similar to a relay. And what you were trying to explain. They have a relay, let's see here. Oh no, I don't think I have it here open. No, they have a relay. It looks like it's like a current type relay. It looks like a heating element with a switch, which was in the base electricity that you did. So instead of a magnetic coil, it was something that heated, and when it got hot, it would cause a switch to close or open. So it's very similar to that.
Yes.
All right, I'm gonna stop here. I don't want to add any more to this. I'll post this online so you guys can watch it again if you want later at another